Unacademy. Let's crack it.
Hi everyone, welcome to our channel, and today I, your host Jaya Bansal, will be taking you to an exciting journey to the coding realm. We will cover top 10 must-know algorithms anyone should know to crack any coding interview. So let's start with the algorithms. First one which we're going to cover is the binary search, and I am calling it today the speed seeker because it seeks to the right place at tremendous amount of speed. So what it does is you need a sorted array first. So let's say you have a sorted array. This is a sorted array, and you need to find an element in this sorted array. Let's say you want to find 35 in this particular array. So what it will do is it will take the middle element and compare 35 with the middle element. If it is smaller, since 35 is smaller than 41, our search space reduces to the left half of the array because the element must be on the left side. And again it will search the middle element. Since 35 is greater than 23, our search space will go to the right side of 23. And now we will again try to find at the middle element, and we found an element which is 35. So this is how binary search works. In each iteration, we are dividing the array in half. That's why we will require log n operations. So if you are doing it in half, it is log n to the base 2. This is the time complexity of binary search algorithm. It is one of the most powerful algorithms for any interview. Second is bubble sort, and I'm calling it today the amusing arranger. It arranges the elements in an array, and it's the most naive and basic algorithm to sort any array. So let's say this is the array you want to sort. Obviously it is unsorted right now. It is not sorted. What do we mean by sorting? We just need to put the elements in the ascending order, right? So what it will do is it will take a bubble, a sliding window of size 2. So our bubble is of size 2, and it will slide this bubble every time in the array, basically n times in the array. And if in that bubble, if the elements are not in the right order, for example here 70 and 41 are not in the right order, we will swap them, right? Because 41 should have come before 70. Similarly, again 35 should come before 70. The order is not right, we will swap them. Again, slide the window. 7 should come before 70, just swap them. Now again, slide the window. 70 and 88 are in the correct place. Now what happens is, in one iteration, the largest element will always go to the end. Because in worst case, what will happen? It will keep swapping and go to the end. So in every iteration of bubble sort, one element will go to the correct place at the end. So after k iterations, the last k elements will be in the correct place. For example, here in 2 iterations, 70 and 88 are sure to be in the correct place. Now in the third iteration, we are doing the same thing. The third highest element of the array will definitely be at the third last place, and so on. So we'll keep doing this. So first time we scanned the array n times, then we did it n-1 times, then we did it n-2 times, and so on. At the end, we will have our sorted array ready. So if you think about it, how many comparisons or how many computations did we do? It's n plus n-1 plus n-2 and so on up to 1, which is big O of n square. This is the complexity of bubble sort algorithm. It is large, okay? So if n is very large, n square will be huge. So bubble sort is a bit slow algorithm. That's why the third algorithm for today, quick sort, it is quick as light. So that's why I'm calling it the lightning bolt. So it does the same task. You will be having an array, unsorted array. It will sort the elements of the array, but in a much faster fashion than the bubble sort. So again, the goal remains the same. You need to sort the array. How quick sort works is you will have a pivot element, left and right pointers. So we can take pivot as any element. We are taking the rightmost element as the pivot. So 23 is our pivot. So since pivot is at right, we will compare it with the left element. And if the order is not correct, we will swap the pivot and that particular element left or right. Now since pivot is at left, we will compare it with the right element. Is the order correct? Yes. So we will move right to the left. So now 23 and 7, pivot was larger than right element, so we will swap them. So basically, pivot will be either at left or right. And if pivot is at left, we compare it with the right. If pivot is at right, we compare it with left. Now, while comparing, if the order is correct, we just shift the left or right pointer, whatever we compared it with. And if the order is not correct, we swap the pivot and that particular element. Makes sense, right? So what happens is after first iteration, 23 goes to the correct place. The pivot will always go to the correct place. All the elements smaller will be to the left, all the elements larger will be to the right. Now in the second iteration, we took 57 as the pivot, and now we are doing the same thing. Notice here, now 57 goes to the correct position. Right? Now again we take the rightmost element, which is 70 as the pivot, and 70 and 88 are not in the right place. We are comparing pivot with left, so we swap them. And now the rightmost element 88, it is the only element, so it is obviously sorted. We don't need to take the pivot. Now we take 35 as the pivot, and we compare it with the left, which is 41, and they are not in the right order. We swap them, and definitely 41 is the only element left here, so it is in the sorted order. So the last pivot we have is 7. Again we compare it with the left. The order is not correct. We swap them. Then we move the right pointer. We hit the left. That's why we stop here. Now the only element left is 12, which is already sorted. Like the single element is anyway sorted. So that's how quicksort works. Take a pivot, compare it with left or right. If the order is not correct, swap them. So the time complexity of quicksort, the amortized analysis is big of n log n. So the details is not the part of we don't have time to cover all the details. I will make smaller videos of all these algorithms later. So the next algorithm that we are going to cover is the Dijkstra's algorithm, and I am calling it today the shortest path finder. What it does is, in a weighted graph, it will calculate the shortest distance of all the nodes from one particular source node. For example, in this graph, let's say we want to find the distance of every node, the shortest distance from node 1. So in the initialization step, what we will say is the distance of node 1 from node 1 is 0 and all other nodes is infinity. Okay. Now what we will do is we will take node 1 and take all the outgoing edges from node 1. So we will explore all the nodes. Let's say we explore node 2. Now the distance is 7. So 0 plus 7 is less than infinity, which is the already present distance. So we relax this edge. This is called relaxation. Okay, so we will relax this edge and we write the distance of node 2 as 7. Similarly, we go to node 3. Now 0 plus 9 is less than the already present distance, which is infinity. So what we will do is we will again relax this node and write the distance of 3 as infinity. 9. And similarly, now we go from node 1 to node 5, which is the next node in order. And the already present distance at 5 is infinity, but now the new distance is 0 plus 12, which is less than infinity. So we will basically replace infinity with 12. Now what we do is we take the next node, which is the node with the least distance from node 1. Right now the least distance node is node 2 with the distance 7. So we take that particular node. Again we do the same thing. We take all the adjacent nodes from node 2. So let's say we take the node 3. Now the distance now via 2 becomes 7 plus 7, because 2 is at distance 7 and 2, 3 edge is 7. So 7 plus 7 is 14, which is greater than the already present distance 9. So we will not relax this edge. We will say that 9 is the distance which is correct, which is directly via 1. Similarly, from 2 we will go to 4. The distance from 1 to 4 via 2 is 7 plus 12, which is 19, which is less than the already present distance, which is infinity, right? So we will replace infinity with 19. Now 2 is also exhausted. Now we take the next node with the least distance, which is node 3 with distance 9. So we do the same process. From 3 we will go to 5, 6 and 4, and we will see that we can relax the edges or not. 9 plus 2 is less than 12, so we will relax it. We will make the distance as 11. Similarly, again from 3 we will go to 6. 9 plus 8, 17 is less than infinity, so we will relax this edge and we will mark the distance to 6 as 17. And similarly from 3 we will go to 11. Again 9 plus 11. Actually right now the distance is 19. 9 plus 11 is 20, so we will not relax this edge. We will keep it as 19. Again we go to the next node with the least distance, which is 5. So from 5 we go to 6. Now 11 plus 3 is less than 17, so we relax this edge and we say that the distance to 6 now becomes 11 plus 3, which is 14. And last step, from 6 we go to 4. We see that 14 plus 6, which is 20, is actually greater than 19, so we don't do anything. And these are our shortest distances from node 1. That's how extra works. See, the implementation in any coding language is a different thing. You can do that. We will make a separate video for that. Right now, this video aims a short introduction to every algorithm, the top 10 algorithms, okay? So the time complexity of this algorithm actually depends on how you're implementing it. So if you're implementing using priority queue, the time complexity is big O of v plus e log v, where e is the number of edges and v is the number of vertices. I will discuss this in a separate video. So on number 5, we have dynamic programming, and I'm calling it the problem solver extraordinaire. It can solve like any problem, like it's like solve n number of problems, okay? It's not an algorithm, it's a strategy. And this is just a small list of problems which are very well known and are asked in interviews, which can be solved using DP. So I will not be solving a problem today. I will make separate videos on all of these problems, on how to solve the problems on DP. Videos like this, short videos. So for now, like solving each one of them is out of the scope of this video. I'll just briefly explain how DP works. Okay, so you're given a problem to solve, like 0-1 knapsack, any problem. You break it into n sub-problems. You try to solve each one of the n sub-problems. But the thing is that the exact task where DP works is you can actually create a lookup table or memorize the outputs. So if the sub-problems repeat, you don't actually solve the sub-problems again and again. Try to remember the solution to the sub-problems. Like create a lookup table. If you can do that, you can solve the problem using DP. So the next algorithm is the merge sort algorithm, and I'm calling it the harmonious merger. There is a very interesting concept on how merge sort works, and that concept is called divide and conquer. It divides the array in equal halves and then conquers it, then sorts it. So let's say this is the array and our problem statement is same. We want to sort this array. So we'll divide the array into half. Then again we will divide these array into half. So basically so we are again partitioning these arrays into half, and we keep doing this till we get single elements. So this is how we have it right now. Then now at this base condition we conquer them. So now we merge 12 and 57. We are trying to create a sorted array, small sorted arrays. So then we sort 41 and 70. Then we sort 35 and 7. So 7 should come before 35. Then we sort 88 and 23. So then it becomes 23 and 88. Now we have sorted arrays of size 2. So we will merge them. So we merge 12, 57 and 41, 70. So we compare 12 with 41. Since 12 was lesser, 12 comes here. Then we compare 41 with 57. Then we compare 57 with 70. And that's how we are actually merging these two sorted arrays. This can be done in order n time. If we have two arrays, sorted arrays of size n, we can merge them into another sorted array of size 2n in order of n. Okay, so that's actually what we are doing. Now we have two sorted arrays of size 4. We will merge these two. So we compare 7 with 12, 7 is smaller. We compare 12 with 23, 12 is smaller. We compare 23 with 41, 23 is smaller. We compare 35 with 41, 35 is smaller. Now we compare 41 with 88, 41 is smaller. 57 comes, then 70 comes, then 88 comes. This is merging of two sorted arrays. That's how merge sort works. So if you think about it, again, it's a very interesting problem, like that time complexity of merge sort. We can create a entire video on it. Very interesting problem, very commonly asked interview problem again. But yeah, the time complexity of merge sort is bigger of n log n, and we will prove it in some other video, okay? Cool. So the next algorithm, number 7, is the breadth first search, commonly known as BFS, and I'm calling it today the Frontier Explorer. So what it does is, it explores the entire tree or graph. I'm showing you this algorithm on tree, but this works with graphs as well. So in a tree, let's say you want to find 35. An element 35. What it will do is it will search on breadths. So it will take a starting element, let's say the root 41. It will try to search the breadth. So it will search all the child of 41, 70 and then 7. Then it searches the children of 70, 57. Then it searches the children of 7, which are 88, 23 and 69. Then it searches all the children of 57, which is 12. Then it searches all the children of 88, no children. Then it searches the children of 23, which is 35. So basically search all the children of a node and then move ahead. That's why breadth first. Okay. So this can be implemented in many ways. If you implement it using queues, the time complexity will be big of v plus e. Again, this can be a discussion of some other video, but this is how BFS briefly works. So the next algorithm is in line, which is algorithm number 8, is depth first search. Okay, these algorithms are very important. Okay, they have been asked in interviews in number of times, and I'm calling DFS today the adventurous voyager. So what it does is it searches the depth of the tree first. So let's say again in the same tree I want to find the element 35. So we start at the root node, we go till the last element. Okay, we go till like we go deep. So from 41 we go to 70, then we go to 57, then we go to 12. So basically we are taking up all the left half of the tree. Now we didn't find the element, so we backtrack to the root. Okay, then again we go to the right element 7, then we go like to the depth, which is 88. We didn't find the element, we backtrack to 7, then we go to 23, then we go to 35, and actually we have found our element. Okay, so this algorithm also has the same time complexity. Generally DFS is implemented using stacks or using recursion. Actually recursion, like anyways, is a stack, right? So the time complexity remains same, it's big of v plus e. We will analyze all these algorithms in detail in individual videos later, okay? Like how to code them, how the time complexity actually works. So the next algorithm in line, algorithm number 9, is hashing. Very important for interviews. They will ask you why, like how hashing works. And I'm calling it today the efficient data organizer. So let's say I have 5 strings. Let's say I have n strings, I want to store them. Let's say I've like stored the strings, but like the query which I'm getting is find one particular string. Let's say I'm getting a lot of queries like find this string, and if let's say I've put them in memory in any order. So if I want to find a string, I will have to search each one of them, and it will take n operations. Okay, I will search like is A, B, E, F, G. This is not correct. Okay, this is not efficient. What we can do is we can create a hash function from a string to an integer. So let's say right now for this problem I'm creating a hash function which is the sum of character numbers modulo 7. Modulo means remainder when divided by 7. So for example, like for all these strings I have calculated the hash function for you. Let's say the hash of AB will become 1 plus 2 modulo 7, because A is first character, B is second character in alphabet. So 1 plus 2 modulo 7, which is 3. Similarly, the hash of CD will become 3 plus 4 modulo 7, which is 0. Hash of EFG will become 4. Hash of HIJ will become 6. Hash of KL will become 2. So now what happens is we can create a hash table. So the integers which can be present are between 0 to 6, and this is our hash table. See, there can be collisions in this hash table. Again, there can be caveats which can be discussed in some other video. This is the brief idea how it works. Now let's say I want to find another element, like find if EFG is present or not. I will just calculate the hash value of EFG. It is 4. I will go to the lookup table. At 4, is EFG present? Yes, it is present. So yes, we have found our element. See, calculating hash is a constant time operation, and looking up at the lookup table is also constant time. That's why the time complexity after hashing becomes constant or big O of 1. Very important algorithm, okay? Very important concept. So the last but not the least, and it also has been asked in interviews like many times, okay? Even in Microsoft, I got this question, okay? It is fast exponential, and I call it the flash. It's like super fast. See, most of the concepts here work like DP. So let's say I want to calculate a to the power b. Okay, let's say I want to calculate 3 to the power 8. How will I do it? It is 3 into 3 to the power 7, and I can keep breaking it. Okay, I can take 113. This is the most basic trick that how do you calculate 3 to the power 8, right? Multiply 3 8 times. So basically you will require 8 operations or b operations if you want to calculate a to the power b. If you're multiplying a b times, what you could have done is you can write 3 to the power 8 as 3 to the power 4 into 3 to the power 4. Again, you can write the first 3 to the power 4 as 3 square into 3 square. Again, write the first 3 square as 3 into 3. Don't complete the entire tree. Use memorization, use DP, okay? Now 3 into 3 is 9. So 3 square becomes 9. Now another 3 square also becomes 9. Now 9 into 9 becomes 81. 3 to the power 4 becomes 81. Another 3 to the power 4 is also 81. So 3 to the power 8 is 81 into 81. you actually record only 4 operations, not 8. Okay, you're actually breaking the power into 2 every time. Again, it's like binary search and DP, right? So here actually the number of operations is the depth of the tree, which can be at max log b if you want to calculate a to the power b. Okay, so this was our last algorithm, the 10th algorithm. These are the most basic algorithm algorithms anyone should know to crack coding interviews. Okay, so I'll be leaving you guys today with 2 bonus questions. Okay, I'll be answering them in another video. You try them. You have to write computer program to solve these problems. So first is, you have to calculate the 9 factorial Fibonacci number. Let's say Fibonacci of 3 is what? Third Fibonacci number, which is 1, 1, 2, 2. Okay, so you have to calculate 9 factorial Fibonacci number, and we calculate modulo 6961. And the next problem is you have to calculate 9 factorial modulo 6961. Okay, these are the 2 bonus questions which you have to solve. We will solve them. They are really interesting interview problems. Okay, trust me. So yeah, thank you guys so much to watch. If you like the video, just hit the like button and do share it with all your college friends, company friends. Just keep posting it. Okay. So I'm targeting 10,000 views and 500 likes on this video. If I get that, I will create more such videos because that will be a motivation for me. And I'll be explaining all these algorithms in detail with code. Also, I'll be giving you answer to the bonus questions. Okay, so right now in the comment, write the answer whatever you're getting to the bonus questions. And thanks for watching. Just share this video to as many people as you can. Okay, thanks again. Bye bye. Have a great day.